Okay, so let's get on. So what we're aiming to do in this segment is get some sense of the stability of the equations that we need to look at. Now, if we want to look at stability, we have to first understand, we must first understand the stability of the time exact case, right? Because that is the sort of behavior or the sort of response we are aspiring towards for our system, right? For our algorithmic system, okay? So in terms of stability, let's first understand the time exact case. Right, now we've derived the single degree of freedom modal equations for an arbitrary mode L. Okay, now everything we do holds for every mode, right? Our analysis holds for any mode because we're really working with an arbitrary mode. With that in mind, I can afford, I believe, to drop the explicit use of the modal index L. Okay, right? So I'm going to drop that, right? So from now on, the time for the time exact case, since we're working with a single degree of freedom for the time exact case and for the time discrete case, when we are working with single degree of freedom modal equations, I'm just going to write them as d dot scalar plus lambda d equals 0. Okay. But one more thing. I've got rid of one index L, but I want to bring back another one. The one I want to bring back is I'm going to use H, right? And this is not an index, it's a superscript. Why am I bringing H back here? Remember, H is our old friend, the element size, right? It denotes the element size, the fact of spatial discretization. Why am I bringing it back? Right, it's because our M and K matrices depend upon our discretization, our spatial discretization, right? So the eigenvalues we're working with here are truly the spatially discretized, the eigenvalues corresponding to the spatially discretized system, okay? So let me just state that here. Lambda H is the eigenvalue of a mode or corresponding to a mode that is obtained after spatial discretization. Okay, so the fact of spatial discretization, which shows itself which shows up in the finite element size, is indeed reflected in lambda H. Okay. Alternately, because these are partial differential equations, one could do a fully continuous analysis of them, and then one would have a eigenvalue corresponding to modes, but those would not be discretized modes. Okay, those modes or those eigenmodes would be actually eigenfunctions, not eigenvectors. Okay, so there would be there's a difference. We're really working with the eigenvalues of the spatially discretized system here, and that will show up. Okay, that it's for that reason that I'm bringing back our memories of H here. Okay. All right. So the time exact case is this, plus of course boundary condition, the initial condition, right? So this is that D0 equals D naught, right? On the previous slide, we'd used the modal index L, but we've just decided to drop it here, okay? Without risk of confusion, because everything we do holds for every mode. All right. So what is the stability of the system? How do we know what the stability of the system is? This equation is one of the simpler ODEs you're likely to encounter. Okay, we can directly write down the exact solution of it. Right, so the exact solution is d as a function of t equals d sub 0 exponent of minus lambda h times t. Okay, it's easy enough to check that that is indeed the exact solution. If you plug it into your equations, you will find, and into our ODE, you will find that it satisfies the ODE, and it also respects the initial condition. Okay, just set t equal to 0. On the right hand side, since exponent of minus 0 is 1, you get back d at 0 equals d naught. Okay, so this is the exact solution. All right, now what about lambda h? What do we know about lambda h? It's an eigenvalue of the system, right? What is lambda h? Lambda h turns out to be greater than or equal to 0. Okay, all right. Why is lambda h greater than or equal to 0? We're not going to prove it, but do you know what properties give us this? It is the fact that m is positive definite, right? And k is usually positive definite, but in the most general case, if we want to also allow for insulation along certain directions, if you're talking of heat conduction, or the possibility that there is no transport along certain directions, if you're talking of mass diffusion, then k is positive semi-definite. Okay. Earlier on, we had used the fact that k can pretty much be taken to be positive definite unless you want to really have insulation. We'd use that fact to make the observation that that we are going to get eigenvectors that are linearly independent. Okay. All right. So we have this sort of situation. All right. If that is the case, since lambda h is greater than or equal to 0, what can we say about d, say Tn plus 1, right? And we know what this means. It just means that we're evaluating the solution at time Tn plus 1. What can we say about d at Tn plus 1 relative to d at Tn? Right? And here I'm using the fact that because of the nature of our time discretization and our choice of the progression of time instants, Tn plus 1 is greater than Tn. Right, so let me just recall that also. We are, of course, using here the fact that we are progressing in time. So Tn plus 1 is greater than or equal to Tn. Right, it's greater than Tn. We never use it equal to Tn, because that would mean we have a 0 time step size. Okay. All right. So given this, what should I use in this blank here? I've left a big blank spot between d at Tn plus 1 and d at Tn. What relational operator do I use? Right, because the exponent of a negative argument is less than 1, right? What we see is that this is a decaying function, right? It's monotonically decreasing. Okay? Or another way of looking at it is that d at Tn plus 1 divided by d at Tn is lesser than or equal to 1, provided, of course, d at Tn is not 0. Okay, but nevertheless, it's monotonically decreasing. Right, so we have a monotonically decreasing, time-dependent coefficient for our mode. Okay. All right, and this essentially says that the nature of our heat conduction equation, or the nature of our mass diffusion equation of the kind we're looking at here, is for the solution to tend to decay. Okay, there is no tendency for the solution to tend to increase, provided we have set the forcing equal to 0. All right, and it is in order to expose this characteristic of the equations we are working with that we are considering the homogeneous case. Because clearly you could be supplying heat to increase the to raise the temperature, or you could have a local supply of mass, or again influx of heat or mass in order to push up the temperature or the mass concentration at any point, and therefore these modes could be increasing in a problem that is inhomogeneous. Okay, but we wanted to get to this fundamental characteristic of the equation, so we just assume we are considering the homogeneous case. All right, so why are we doing this? The reason we are doing this is because we want to understand what is the exact behavior that our algorithmic equation should aim to represent. Okay? All right. So with this in hand, let's ask ourselves what the same sort of analysis tells us for our time discrete equation. And this is really quite easy, because the way we've written out the time discrete equation, it is in algebraic form. It just gives us dn plus 1 multiplied by some factor minus dn multiplied by some other factor. Okay, so the time discrete equation, if you go back and look at it in your notes, and I have it right up here in my slides, so let me just flash it up again. It is in the middle of this slide, right, marked out boldly as time discrete equation, time discrete case. Okay, so I'm going to rewrite it using the same notation that we are now following, which is to drop the modal index L, and instead for lambda bring back the superscript h. Okay, so the time discrete case with using this notation is the following. It is d times 1 plus alpha delta t lambda h equals, I'm just moving it to the right hand side, equals dn 1 minus alpha delta t lambda h. Okay, sorry, and here I have dn plus 1. Okay, all right. Now let's try to form that same ratio that we'd formed in the case of the time exact problem, right? So the equivalent ratio to form here is dn plus 1 at divided by dn. Okay, and this, as we see, is equal to 1 minus alpha delta t lambda h divided by 1 plus alpha delta t lambda h. Okay, now in the context of our time discrete algorithmic problem, we tend to call this ratio, we tend to denote it as A. Okay, and A very obviously is picked because because this is really an amplification factor. Right? Inasmuch as it is obtained as a ratio of dn plus 1 over dn, it essentially tells us how is our time discrete solution getting magnified from one time step to the other, right, or getting amplified from one time step to the other. Okay, and you note that A depends upon, if you want to think of it in that way, it depends upon alpha, it depends upon lambda t, and it depends upon lambda h, right? Okay, So what that says is that yes, our integration algorithm matters, right? Whether we're choosing one type of the Euler, one member of the Euler family or the other. Our time step matters for stability. That should not be a big surprise. But interestingly as well, the spatial discretization we've used does matter. Okay, and this is why I took pains to point out that the eigenvalue we're working with for any mode is really a discretized eigenvalue in the sense that it reflects the spatial discretization. All right, and that too does affect our amplification factor. All right, well, let's just do one more thing. What do we mean now by a stable problem? Right, we wanted to reflect what we saw for the time exact case. Okay, so for stability, the requirement we want to have, right, is the following. We want to say that the magnitude of A should be lesser than or equal to 1. Okay? All right. Now, you may wonder why we are going with the magnitude, right? What happens, and why not just say A has to be less than 1? Well, what you're going to see is that this is after all, we're doing approximations here, right? We are constructing the reason we're getting into discretizations is because we want to approximate the time-dependent behavior. Well, one result of that approximation and of that discretization is that it is possible for our solution to sometimes go negative here. Okay, so that is something that we will have to deal with, right? And that's why we recognize that A could be negative. Dn plus 1 over dn could be a negative ratio. The solution can change signs. We're just recognizing that the algorithm may do that, and therefore we are restricting ourselves further by saying that the magnitude of A has to be lesser than or equal to 1. Okay, we are not guaranteed positive solutions always for our time discrete problem. Okay, so when we come back, we're going to end this segment here. When we return, we are going to apply this condition to our time discrete problem and see what it tells us.